Hello everyone, this is Professor Roman, and this is the fourth course in my series, Abstract Algebra Comprehensive Introduction. This course is on field theory. As you know, if you've been following along, there were three previous courses: linear algebra, group theory, and ring theory. Each of the courses is accompanied by a textbook which is available on my website, www.sroman.com. So if you want to follow along the lectures with the book in hand, that's where you'll find the book. The lectures, as you know, if you've watched any of the previous courses, follow the book very closely. As for prerequisites, it's really not possible to study field theory without some knowledge of vector spaces, groups, and rings. Exactly how much knowledge, I guess it's a bit difficult to say. What you can do is start the field theory course, and when you come to something that you're not clear on, related to vector spaces, groups, or rings, you can stop and learn what you need to know. It's going to be a little awkward to do that, but it is possible. I would not recommend, however, starting your study of abstract algebra with field theory. That will be quite difficult. You do need some knowledge of these other algebraic structures. Let's take a look at the table of contents. I'll just go over this briefly just to give you some sense of what is coming. The first chapter is on field extensions, which we did discuss briefly in the ring theory course, but we'll of course go into much more detail here. We'll talk about field extensions as vector spaces. We'll talk about the lattice of subfields of a field, just as we did for rings and groups and vector spaces. We'll talk about special properties of elements of a field, such as algebraic elements. We'll talk about separability. We'll talk about different types of field extensions, such as algebraic extensions, finitely generated extensions. There were some other types we'll talk about later: normal extensions and separable extensions. We'll talk about algebraic closures, splitting fields. We'll talk about transcendental extensions very briefly. The next chapter is on embeddings of fields. Homomorphisms, ring homomorphisms, between two fields must be, if they're not zero, must be injective, and so they're embeddings. So this is really a discussion of what you might call field homomorphisms, but I've not heard that expression before. They're just simply called embeddings. And here's where we can discuss normal extensions. Chapter 3 is quite interesting, I think. It's algebraic independence. It turns out that the notion of dependence and independence is much more general than it is when you study linear algebra, where you talk about linear dependence and linear independence. That's a special case of the general concept of a dependence relation. So we'll take a quick look at dependence relations and what they look like for fields. In the case of vector spaces, they're linear independence and linear dependence. In the case of fields, they are algebraic independence and algebraic dependence. Chapter 4 is very short. It's a beginning of our study of Galois theory. We'll talk about symmetric polynomials and Newton's theorem, which plays a key role in future studies. Then we'll take an overview of Galois theory to give you a sense of what that theory is. And then we'll get into the details, the Galois correspondence, the fundamental theorem of Galois theory, which I split into 3 parts. And we'll talk about the Galois group of a polynomial and the symmetric groups, the Galois correspondence for the general polynomial, the discriminant of a polynomial, and we'll look at a careful analysis of the cubic. Chapter 7 is on roots of unity and binomials. We talk about cyclotomic polynomials. Roots of unity play a key role in the study of Galois theory. And chapter 8 has what I would assume many of you have been waiting for, and that is solvability by radicals. This is where we will prove perhaps the most famous theorem in abstract algebra, and that is that there are polynomials of degree 5 and greater for which the roots cannot be obtained by algebraic formula, similar to the quadratic formula. There's a quadratic formula, a cubic formula, and a quartic formula, but no quintic formula or higher. There are individual polynomials whose roots cannot be computed using the 4 basic arithmetic operations and the taking of nth roots. So they're not accessible, they're not computable by the usual type of algebraic formulas. Chapter 9 is a proof of the fundamental theorem of algebra, and then I have an appendix here which looks at Galois theory, or Galois' contribution, let's say, from an historical point of view, starting quite early in history with the quadratic equation, looking at the works of Vandermonde, Lagrange, and Gauss, which preceded the work of Galois, a little bit of Galois' life history, which is easily found on the internet. So that's what the course will be, and as I said, as I have done before, I'll follow the book quite closely as we go through these lectures. Okay, so let's start looking at Chapter 1. I included here some definitions and some facts from the ring theory course, without proof for the most part. These are things that you should have seen before, so we'll go through them with reasonable speed. First comes the definition of a ring, and that is, as you know, a non-empty set with 2 binary operations, addition and multiplication. If you call the ring R, then R is an abelian group under addition. These are the requirements for an abelian group. Multiplication is associative. There is, for us, all rings will have a multiplicative identity. And then there are distributive laws. A ring is commutative if multiplication is commutative. The well-known matrix rings are examples of non-commutative rings. An element in a ring is a unit, or is said to be invertible if it has a multiplicative inverse. The set of all units of a ring R will be denoted by R star. That's a relatively common notation, I think. A non-zero commutative ring R is called an integral domain if it has no zero divisors. Or another way to say that is to say that the product of any two non-zero elements must be non-zero. A field is a special type of ring. A non-zero commutative ring R is a field if every non-zero element has a multiplicative inverse. Or, equivalently, if the non-zero elements of R form an abelian group under multiplication. I'll generally use letters such as capital E, F, K, and L to denote fields. So a field is a ring in which the operation of multiplication is almost as strong as that of addition, however you want to interpret that. But because it's not quite as strong, because although every element has an additive inverse, 0 does not have a multiplicative inverse. The roles of addition and multiplication are not symmetric. And this difference has a profound effect on the nature of fields when compared to arbitrary commutative rings. Here's a couple of examples. Because of the existence of multiplicative inverses for the non-zero elements, a field has only two ideals, the zero ideal and the field itself. So in particular, the notion of quotient field is essentially meaningless. It's trivial. Also, every non-zero ring homomorphism between fields has trivial kernel, and so is injective, is an embedding, in fact. And so one never hears the phrase field homomorphism. You hear field embedding. Because the zero element has no multiplicative inverse, the Cartesian product of two fields, F cross G, is a ring but not a field. For example, the product of these two elements of F cross G, these are non-zero elements, the product is 0. So there are 0 divisors in the Cartesian product. If Fe is a field extension, I defined this for you in the ring theory course. All this means is that F is a subfield of E. So if we have a field extension, Fe, it sounds silly to read this as F less than or equal to E, so I'll just read this as Fe. Then E, the bigger field, can be viewed as a vector space over F. And surprisingly, it almost seems like we're giving up some structure here. Well, we give up multiplication, but we get scalar multiplication. This viewpoint turns out to be very useful in the study of fields, and as we'll see as we proceed. So these are some examples of behavior that's radically different in fields when compared to arbitrary commutative rings. A finite integral domain is a field, and the ring Zn, these are the integers from 0 to n minus 1 under multiplication and addition mod n. This is a field if and only if n is prime. These are proved in the field theory course. You shouldn't have too much trouble, and suggest you try proving them yourself. As I mentioned several times in the other courses, when I give a theorem that has no proof, it's an invitation for you to supply a proof. It's good practice. I also talked in the ring theory course about the characteristic of a ring, the smallest positive integer c for which c times 1 equals 0. C times 1 here is the sum of c copies of 1, if c is positive. Or equivalently, for which CR is only containing 0, is called the characteristic of R. If no such smallest positive integer exists, then R has characteristic 0. And we'll denote the characteristic of R by this symbol here. All fields have characteristic 0 or a prime. Here is a result we proved in the ring theory course that's actually very useful. If F is a field and S is a finite subgroup of the multiplicative group F star of non-zero elements, those are the same as the units, then S is a cyclic group. Okay, I'll read that again because this is important. You have a field F. F star is the set of units, or equivalently the set of non-zero elements. A finite subgroup of F star. So this is under multiplication now. A finite multiplicative subgroup of F star must be cyclic. In particular, if F is a finite field, then F star itself is a cyclic group. Generally speaking, fields can be classified into 3 types. Fields of characteristic 0, such as the common number fields, rationals, reals, and complex. Also, the field of rational functions in an independent variable over Q, R, or C. These are fields, the field of rational functions. T here is an independent variable. We'll define precisely what we mean by independent variable later in the book. Field theory is precisely the right place to define the notion of independent variables. But for now, you can just rely on your intuition. Second type, finite fields, such as ZPN. P is prime, n is bigger than or equal to 1. And as a matter of fact, there is, up to isomorphism, exactly one finite field for each prime power. And that's all the finite fields there are. Third type, the rest of the fields, infinite fields of prime characteristic, such as ZP of T, the rational functions again, in T over the field ZP. It turns out, which is probably not surprising, that fields of characteristic 0 tend to be more well-behaved than infinite fields of prime characteristic. What's a little surprising, perhaps, is that finite fields also tend to be more well-behaved. As an example, we'll see in a theorem coming up later in this chapter that in fields of characteristic 0 and in finite fields, all irreducible polynomials are separable. Separable means no multiple roots. But look at this example, Z2 of T squared. This is an infinite field of characteristic 2. These are the rational functions in T squared over Z2. This polynomial, x squared minus T squared, is irreducible. You cannot factor it over Z2 of T squared. But over a bigger field, z2 of t, it factors this way. So it has a double root in the larger field. This behavior cannot happen for fields of characteristic 0, nor for finite fields. Okay, let's give the official definition of field extension. A subfield of a field E is a non-empty subset F of E that is a field in its own right under the restricted operations from E. This is exactly the same kind of definition we gave for subspaces of a vector space, subgroups of a group, subrings of a ring. Notation here is a little different than those other cases. F less than or equal to E, or E bigger than or equal to F. Field extensions are so important in field theory, so ubiquitous, that this notation is warranted. E is called an extension of F, and FE will be referred to as a field extension, or simply an extension. F is the base field. If FE is an extension, but F is not equal to B, if it's a proper subset of E, then I'll use the strictly less than symbol and call this a proper extension or a non-trivial extension. There's more terminology here that it may seem like a lot, but you'll get comfortable with it fairly quickly, I think. If FE is an extension and K is a field lying between F and E, we will call K an intermediate field of the extension. A sequence of field extensions is called a tower of fields. And each individual extension, Fi to Fi plus 1, is called a step in the tower. The length of a tower is the number of steps, which in this case would be n minus 1, and we also may have a proper tower where all the steps are proper. It's going to be convenient to say that an extension, Fe, contains an element alpha if alpha belongs to E, and contains another extension, KL, if K and L lie in between F and E like this. And here's a theorem that also is a direct analog, has a direct analog in the other branches of algebra we studied. A non-empty subset F of a field E is a subfield of E if F is closed under subtraction, multiplication, and the taking of multiplicative inverses of non-zero elements. We spent a fair amount of time in the ring theory course discussing the theory of polynomials over both rings and fields. So let me go over some of that quickly, some information we may need for this course. The greatest common divisor of two polynomials, f of x and g of x, over a field F is by definition the monic polynomial with the property, and it is unique. So I say the monic polynomial p of x over f, for which p of x divides f and divides g, and any other common divisor, r of x, that divides f and g, divides p of x. So that makes it the greatest common divisor. The reason it's unique is because we require it to be monic, so its leading coefficient has to be 1. Because the ring of polynomials over a field is a principal ideal domain, we know that every pair of polynomials, not both zero, has a greatest common divisor, d of x, and it is in fact the monic generator of the ideal generated by f and g. And so there are polynomials a of x and b of x for which the GCD is this polynomial combination of f of x and g of x. It's an interesting fact, maybe a surprising one, that the greatest common divisor of two polynomials is field independent. So if we have two polynomials f and g over a field F, those polynomials can also be thought of as polynomials over any bigger field than F, over any extension of F, also over any smaller subfield of F that contains the coefficients. So there's a lot of fields that you can use for the base field of the two polynomials. But the greatest common divisor lies in this ring k square bracket x. It's the coefficients of the greatest common divisor are in fact in the smallest subfield of F that contains the coefficients. And so they're in all of the fields. Their coefficients are in all of the fields that extend that one. This has a somewhat surprising corollary. If f of x and g of x are polynomials over f, and e is an extension of f, then f and g have a non-constant common factor over the bigger field e, if and only if they have a non-constant common factor over the smaller field, f. Okay, now we have to be careful here. I didn't say that it's the same non-constant common factor. It's the existence of some non-constant common factor that is field independent. Just the existence, not the actual common factor. So just to illustrate, if you look at these two polynomials, they have a, if you think of these as complex polynomials, then x minus I is a factor of both of them. So they have a non-constant common factor over the complex. Therefore, they have a non-constant common factor over the reals and over the rationals. It's not x minus I, it's x squared plus 1. This is worth thinking about until it's pretty clear in your mind what's field independent and what's not field independent. But because of this fact, we can define two polynomials f and g to be relatively prime if they have no non-constant common factors, period. Or in fact, over any field containing the coefficients of f and g, and therefore over all fields containing the coefficients of f and g. We also have Bezo's identity, which we used quite a lot in the ring theory lectures. If f and g are polynomials over capital F, they are relatively prime if and only if there exist polynomials a of x and b of x, again, over the smallest subfield of F containing the coefficients of f and g, for which this equation holds. It is a fundamental fact that every non-constant polynomial over a field F has a root in some field, some extension of F. And here is the theorem. Let f of x be a non-constant polynomial over field f. Then there exists an extension E of f and an alpha in E for which f of alpha is 0. I proved this in the ring theory course, but I'm going to duplicate at least a portion of the proof here because this is so important to us. We can assume first that f of x is irreducible, otherwise we can just take an irreducible factor. Therefore, the ideal generated by f of x is a maximal ideal of this ring of polynomials. So the quotient is a field. This is the quotient ring. Moreover, this is the canonical projection mapping f of x to E. Pi of a polynomial p of x is simply the coset with representative p of x. If we restrict this to the base field f, we get a map from f to E and does the same thing, but only to elements of f. This is in fact an embedding of f into E, and I'll let you check that. Therefore, E is a field extension of the image pi of f. But E contains this coset, and this is in fact a root of f of the image f pi. This is the notation we used, f super pi. Pi here is a map. This just means take f and apply pi to all its coefficients. And I'll let you go through this yourself. So what this shows is that there is this field pi of f, which is isomorphic to f, and it has an extension E, in which the image of f has a root. Now it's customary, if you look through books on algebra, to say, well, we're done. We're done up to isomorphism, and that's good enough. Okay, so we're going to consider this theorem proved. But if it bothers you, I did explain how to avoid making this small leap in the ring theory volume. Okay. Corollary: if f of x is a polynomial over f, non-constant, then there exists an extension of f over which f of x splits. In other words, it factors into a product of linear factors. Somewhat more generally, for any finite family f of non-constant polynomials, there's an extension over which every member of the family splits. So we'll just say the family splits. This is a very minor extension, and I'll let you think on why that is. As I mentioned before, field extensions define vector spaces. If Fe is a field extension, then E can be thought of as a vector space over F. F becomes the field of scalars. Multiplication, scalar multiplication, is just ordinary multiplication by a vector in E and a scalar from F. So R is an F, that's a scalar. A is an E, that's the vector. Ra belongs to the vector space E. And again, I'll say, it might seem quite surprising, but this is a very useful point of view in the study of fields. And that will become apparent in due course. The vector space dimension of E over F is denoted this way. It's square brackets E colon F, and it's called the degree of E over F. So for example, the degree of C over R is 2. C is a two-dimensional vector space over R. If T is an independent variable, then this vector space is infinite dimensional, this rational vector space. Just a note, whenever I write this expression, it's with the understanding that E and F are fields and that FE is a field extension. I included this definition just for convenience. If FE is a field extension and B is a basis, and by that of course I mean a vector space basis, a linear basis for E over F, then we'll also say that B is a basis for the extension. Just a convenience. If G is a spanning set for the vector space E over F, then I will write E equals angle brackets sub F. The angle bracket notation we used in the vector space course to denote subspace spanned by. Now, degree turns out to be multiplicative, and this is a critical fact, very useful. If we have this short little tower of length 2, so F, K, and E are fields, and if the set alpha I is a basis for the upper step, so that means a basis for E as a K vector space, and the betas form a basis for the lower step, basis for K as an F space, then the products of these basis vectors, remember everything's going on in a field, so we can take products of vectors here. These are distinct, and this set of products is a basis for the full extension, FE. And it will follow from that pretty easily that degree is multiplicative, so the degree of E over F is the degree of E over K times the degree of K over F. The proof here is not really very deep at all. It's just that the notation's a little unfortunate. It makes it look worse than it is. For the linear independence of C, if we have an F linear combination, so the aij's are in F, we want C to be linearly independent over the small field F. And this is a finite sum, the finite number of terms, of course. Then by regrouping here, pulling out the alphas, which are the basis vectors for the upper step, the coefficients must be 0. These coefficients belong to the intermediate field K, but the the alphas are a basis for E over K, so they're K linearly independent, so these coefficients must be 0. But now this is an F linear combination of vectors from K, and the betas here are F independent, and so all the aij's are 0. So that takes care of linear independence. As far as spanning, if gamma is in the big field E, then there exists coefficients from the intermediate field K, for which gamma is a linear combination of the alpha i's, but each alpha I is an F linear combination of the betas, and so gamma is an F linear combination of the products, the alphas times the betas. Part 2 follows easily, and I'll let you think on that. I would strongly suggest that you prove this yourself from scratch, because it's not terribly difficult, but it's good practice in dealing with all this notation. Here's a corollary, which I said it was useful. Frankly, I can't remember how many times I used it. It comes up once in a while, I guess. Fe is an extension. If the degree of k over f is equal to the degree of k over e, and they're finite, then f equals e. Similar statement regarding the upper fields here. Let's conclude this lecture with a discussion of the prime subfield of a field. If f is a field, then f will contain a smallest subfield. One way to see this is to note that the intersection of any family of subfields of f is another subfield. We've discussed this in the other courses. That makes the collection of subfields of a field into an intersection structure. And I'll talk about that again a bit later. But the point is that if we intersect all of the subfields of f, we will get another subfield, and that, of course, will have to be the smallest subfield of f. That argument shows that the smallest subfield does exist, but it doesn't tell us anything about what it looks like. So, theorem. If the characteristic of f is 0, oh, by the way, I should have said this, the smallest subfield of a field f is called the prime subfield of f. So, if the characteristic of f is 0, the prime subfield of f is isomorphic to the rational numbers. And it's customary to think of the rational numbers themselves as embedded in f. If the characteristic of the field f is prime, p, then the prime subfield of f is isomorphic to zp. And again, it's customary to think of zp as actually the prime subfield of f. As for proof, suppose first that the characteristic of f is 0. Then f will contain the distinct elements 1, 2 times 1, 3 times 1. Now what this means is 1, 1 plus 1, 1 plus 1 plus 1, and so on. It'll also contain their negatives and their multiplicative inverses, and so it will contain all elements of the form a times 1 over b times 1, where a and b are integers and b is not 0. So this is how we construct essentially the rational numbers inside f. So f contains an isomorphic copy, call it Q, of the rational numbers. And this map, phi, from the rational numbers to this subfield Q, sending a over b to a times 1 over b times 1, is a ring isomorphism. Also, any subfield of f has to contain 1 and therefore Q, and so that means that Q is in fact the prime subfield of f. I'm going to leave you to construct a proof for characteristic of f equals p. It's rather short, as you can see it here. It's worth pointing out that the rules of algebra can look a little strange in the context of fields of prime characteristic. And so, just as an example, if F is a field of prime characteristic P, then for any two elements alpha and beta of F, the sum alpha plus beta raised to the power p to the n is just alpha to the p to the n plus beta to the p to the n, and similarly for alpha minus beta. All the other terms in the binomial formula will be 0, and this is the proof here. It hinges upon the fact that p divides the binomial coefficient p choose k for k bigger than 0 but less than p. And I'm going to leave you to sort out why that is. Okay. These formulas are actually quite useful. Here's an example. Let F be a field of characteristic P. The Frobenius map, which I'm calling sigma sub P, is simply raised to the pth power. So sigma P of alpha is alpha to the P. This map, because of these formulas, this map is injective. Its image, of course, is the set of all pth powers of the elements in F. Now, the point here is that if F is a finite field, then injective maps are also surjective, and so F to the P is F. The image of the Frobenius map is all of F. The Frobenius map is now an automorphism of F, and in particular then, every element of F has a pth root in F. And that's a significant fact, not easy to prove by other means.